Okay, so to move on from classical physics into quantum mechanics, we need some mathematics that's going to give us discrete energy levels. All of you are happy with this idea that the electron's going to be in state 1, or state 2, or state 3, and not exist in between. So we need mathematics that will yield that and match the atomic spectra that we get from the Balmer lines as the hydrogen atom, or any number of the element's atomic spectra. Okay, so the way we do this is through what's called eigenvalue equations. So an eigenvalue equation. So there's a couple of parts to an eigenvalue equation. I'm going to write out an example and I'm going to take you through it. Okay, so, and by the way, the Schrödinger equation is an eigenvalue equation. Spoiler alert. So the first thing we have is our function. Okay, so this function, I'm going to give an example, is going to be e to the minus 2x. Okay, so this is called an eigenvalue, or sorry, an eigenfunction. And this function, if it happens that when you have a operator operating on the function and it yields a different value, times f of x, then you have an eigenfunction equation. All right, well, what is this a? This is your operator. And I'm going to give the example of d dx. So an operator is going to be something that operates. So my operation that I'm going to do on my coffee is going to be drink my coffee. So anytime coffee comes near me, me being the operator of coffee drinker is going to drink the coffee. They can be any task. If my operation, instead of drinking the coffee, was pouring the coffee out, I would not be a good coffee lover. But that could be my operation. So the same operation is always going to happen with that particular operator. You're familiar with this operation, d dx. That's taking the first derivative of the function. Okay, so let's just operate on this particular function. So if I operate, so if a operates on f of x, that means I'm going to have d dx of e to the minus 2x. Okay, the derivative of anything in the exponential is equal to the exponential, again, multiplied by the derivative of the numerator, or not the numerator, but it was in the exponent. So the derivative of minus 2x is minus 2. Go team. I really hope that you're all shouting this out. That would be awesome, actually. Just give a shout out. Whatever. So a operates on f of x. My operator, d dx, operates on my function. Then what it gives me is a value and the function back again. Hooray! So the function giving the function back again through the operation is what says that we have an eigenfunction equation. The value here is called my eigenvalue. Okay? Let me show you an example when you do not have an eigenfunction equation. So a, f of x, actually let's call this g of x. So let's say that a is still the d dx, but let's say g of x is, I don't know, g of x equals 2x. Why not? All right, so go ahead and operate on 2x with our operator, and I'll do the same. Cool. So d dx of 2x, so the derivative operating on our function 2x, gives us 2. Notice how there's no x anymore. So because there's no x anymore, there's no g of x here. This is not eigenfunction. So it's not an eigenfunction equation. It's not an eigenvalue equation. Cool? Okay. So those are, and then I give some examples in the notes. By the way, I'm on page 18 and 19 in the notes. And I give some examples of how you can use operators. Your homework, you're going to dive deep into operators. Okay,